Good morning, everybody. Today, we're going to work on our first lab session on reinforcement learning. So I suggest you to open your editor, and we're going to start by looking at this file called dpendulum.py, which is inside org/rl. So I suggest you to open this file, and then we're going to spend a few minutes just going through the code to understand the environment we're going to work with. So this is the system that we want to control, and we're going to stick to this system for the whole sessions. On every session on reinforcement learning, we're going to work with this one because they are very computationally demanding, the reinforcement learning algorithms, and so we cannot afford in class to work with a large system. We have to work with a single pendulum, and this is the environment that we're going to use. So this is a discretized pendulum environment because the reinforcement learning algorithms that we are going to study at first are all assuming that state space and control spaces are discrete. So we have a finite number of possible states and a finite number of possible control inputs. So we need to discretize everything by gridding. So we're going to decide how many possible states and how many possible control inputs we want to use when discretizing. These are these numbers here, and Q defines in how many discrete values we want to discretize the continuum of possible joint angles. In this case, the default value is 51. For the velocities, we are using a coarser grid, so only 21 points. And for the control inputs, even coarser, only 11 points. For the control input is much less critical to be coarse. That's why we only use 11 points, because actually the control inputs, they are chosen by us. So if you want to decide to only use 11 possible values for the control inputs, well, that's too bad for us, but that does not affect negatively the accuracy of the solution. We are just limiting what our controller can do, but there is no error in doing that. There is just basically suboptimality. Whereas discretizing the state, that comes with an error in the dynamics. Okay, so that's a bit more critical, and so typically we're going to use more discretization points for the states than for the control. The joint velocities and torques, they're also going to be saturated. So joint velocities, if they reach a certain limit, then they're going to saturate at that limit. We're not going to allow them to overcome that limit. If we want, we can add Gaussian noise, since reinforcement learning works with stochastic environments in general. But, well, we are not going to do that, not at first, at least. And then the cost, which is defined below, then we're going to see it, is going to be simply -1 if the pendulum has reached the goal state and 0 otherwise. And then, of course, since the objective is to minimize the cost, the best thing to do is to reach the goal state as soon as possible. And we can immediately see a difference with respect to the control, optimal control setting. Would this cost be okay in optimal control? A cost that is -1 if you are at the goal and 0 otherwise. Would this work? Why not?
Because I want to minimize the cost variables. The cost is -1.
If the cost is -1,
minimize cost function normally.
Yeah.
And then if you have a goal is less than like -1 is less than 0, so you can minimize that.
So I mean, I see what you mean. You mean that if the cost is a constant, which doesn't depend on the state, then you cannot minimize it because it's a constant. But the cost here is not a constant. It's a function of the state, and it's -1 if the state is at the goal state, and 0 otherwise. So you can minimize it by reaching the goal state.
What I meant was normally you try to minimize the cost function.
Yeah.
The goal is less than minimizing its purpose.
You mean the problem is that the cost is negative? Okay, so then we could shift everything to be positive and say that the cost is 0 if the goal state has been reached and 1 otherwise. Would that work? No, it wouldn't. It's exactly the same. The problem is not that we have a negative value. Okay, why? I mean, that's true, but why? I need to get to the root of it.
Everyone's the same. Everything does the same cost.
Well, no, if you reach the goal, then you have a better cost.
You cannot use numerical method to find the minimum because it's just 1 point. So if you change the states in order to try to reach the minimum, the cost doesn't change, so you can find it.
Yeah, that's true. But why? What's the root reason?
And for example, using gradient descent,
Uh-huh.
you cannot use it because if you start in 1 point, which is not the minimum, you will stay there because it's a local minimum.
Okay, so what you're saying is that the gradient is 0 everywhere. True, that's kind of what I was looking for, but there is also another issue, which is always related to the gradient. What's the gradient at the goal? It's non-differentiable. It's a discontinuous function, which is 0, 0 everywhere, and you have just 1 point where it's -1. There is no gradient. Well, everywhere the gradient exists, but it's 0, so it doesn't give me any information on where I should go. And at the goal, which is exactly the point I want to reach, there is no gradient at all because it's undefined. So this doesn't work with optimal control, with gradient-based optimization. But with reinforcement learning, no problem. You can have non-differentiable cost. You can also have non-differentiable dynamics, which makes it very interesting for robotics, because when you have contact, impact, this kind of stuff, dynamics is non-differentiable. And reinforcement learning can deal with that beautifully. Optimal control, much more difficult. So this is the constructor of the object where you specify all the parameters. Well, the discretization points, we already covered that. Maximum velocity, maximum torque, time step for the integration, which is very large, but in this case, we don't care too much. Number of inner time steps in case we want to then use an integrator with a finer time step when integrating. And then here we can specify the standard deviation of the noise, which may be added to the dynamics. In this case, it's 0 by default, so we are not adding any noise, so the system is deterministic. Okay, and then, well, here we define what is the goal state. which is basically 0, 0. And very important, here we have these functions, which I've defined to switch from discrete to continuous value of the state and the control. So these 4 functions here, they go from continuous to discrete. So for instance, the first one is called C to D Q. So continuous to discrete Q takes as input the continuous value of the joint angle, and it gives you as output an integer value which corresponds to the discrete state space. So we need to map from continuous state space, which is the one we use for computing the dynamics of the system, to discrete state space, which is the one that is used by the algorithm. So this is going to return a value which is between 0 and the maximum number of discrete joint angles, which in our case is going to be probably 51 because that's the default. So it's going to be between 0 and 50. So 0 represents the minimum joint angle, 50 represents the maximum joint angle, and then everything in between is linearly interpolated between these two. So and if you look at what it does, well, there is a shift of pi for some reason, and then it does the modulo operator over 2 pi. So if you are above 2 pi or below 2 pi, it gets wrapped between 0 and 2 pi. And then you just divide Q by dQ, which is a discretization step for the joint angle. You take the floor, so if that division gives you a floating point, you approximate it to the closest smaller integer, and then you convert it to an integer. And then again, just to be sure, you do the modulus operator with respect to NQ. So in case it's above or below NQ, between the range 0 and Q, it gets wrapped again in that range. And then we do the same thing here for the velocities, the same here for the torques. And the last one, which is simply called C to D, it does the same, but for the whole state vector. So for a 2-dimensional state vector containing position and velocity, it calls the 2 above methods for computing the discrete joint angle and the discrete joint velocity, and puts them together in an array of 2 integer values. And then we have 4 methods which do exactly the same thing, but in reverse. So they convert from discrete to continuous. So these ones are going to take as input the discrete values, and they're going to convert them to continuous values. So they do exactly the inverse operation. And then we have another 2 methods which do kind of similar stuff. And this is maybe where it is a bit less obvious. But what we have done so far in terms of converting from discrete to continuous is not enough, because the state is 2-dimensional. And when we convert it from continuous to discrete using the methods we have seen, we get 2 integer values. But instead, what we want is a single integer value representing the state. Okay, because that's going to make our computation much easier rather than working with 2 integer values. Typically, you want to enumerate your whole state space with a single integer. There is no reason why you should use 2. So here we convert from 2-dimensional discrete to 1-dimensional discrete. Okay, it's as if you have a matrix. You can represent every element in the matrix by looking at the row number and the column number. So you're identifying every element with 2 integers. That's one way to do it. Or you could just assign an integer to every element of the matrix. So you start with the first row, for instance, 0, 1, 2, 3, and then you move to the second row, 4, 5, 6, 7, third row 8, 9, 10, 11, and so on and so forth. So basically here we are switching from the row column indexes to a single index for representing all the elements of the matrix. And this is basically how we do it. We simply take the first index and we sum to that the second index multiplied times nq, which is the number of values for the joint angle. And the second method here, I to x, does exactly the inverse operation. So it takes a single index and it computes the two indexes, always in integer notation. So all these methods here, we're going to use them a lot because we will need to go back and forth from continuous to discrete for implementing the algorithm. Well, not a lot, but a few times we will need to do that. So just remember them. Then we have a method for resetting the state of the environment, which can either take the state you want to reset the environment to as an input, or if you don't provide any state, it just resets the environment to a random value. Then we have the step method, which steps the dynamics forward by one time step. So it integrates the system and it also computes the cost. So here we can see the definition of the cost. Cost is equal to -1 if the state is equal to the goal, otherwise is equal to 0. So this is a way to do an if in one line. I think it's the first time that we see it. And then it calls the dynamics and it returns the new state and the cost. We have a method render for displaying the robot in the viewer. We have the dynamics function, which works with the integer values of the state and the control as inputs. Those values are converted to continuous. Then we evaluate the dynamics using the continuous state and control. And then we convert back the new continuous state to integer. And we return that. And then last, we have a couple of functions for plotting the value function associated to the pendulum using a two-dimensional color map. And similarly, we have another function for plotting the policy function, again, as a two-dimensional color map. So these are just utility functions for visualizing what's going on inside the algorithm as we compute stuff. We can do the same with the Q function, but we are not going to use it today because we don't use the Q function in dynamic programming. We're going to use that later when we do reinforcement learning. And that's it. And below there is just a test. So this is our environment. Any question on this before we move on? So mainly it's a wrapper over a standard like a simulator, which does all the conversion from discrete to continuous spaces. So the first exercise is, of course, X0 policy evaluation, which is in the same folder. And the objective of this exercise is to implement policy evaluation for the discrete pendulum environment we have just seen. So policy evaluation, it's a quick reminder what it is. You're given a Markov decision process, which in our case, it's a pendulum, and a fixed policy, which in our case is the one defined here. It's the first function you can see in the script. And you want to compute the value function associated to that policy. So this policy is a policy that I designed by hand to try to stabilize the pendulum in the top position. So it's trying to do the classic like swing up task, where the pendulum, regardless of where it starts, it tries to go to the top position and stays there. And yeah, designing a policy by hand to do such a thing is harder than I expected. So you will see that my policy performs quite poorly. And it's based on this four if statements. So depending on which state I am in, which region of the state space I'm in, I'm applying a different strategy. So if the idea is that if the joint position is close to 0, where 0 is the top position, then I do a PD. So I have minus Kp times Q minus Kd times Q dot. Because a PD should work well when you're close to the top position. And here I compute the value in continuous space. And then I use this method, C to D U, to switch the control input from continuous to discrete. If I'm not close to the top position, then I look at the velocity. If the velocity is positive, then I accelerate as much as possible by applying the maximum torque. And if the velocity is negative, then I decelerate as much as possible by applying the minimum torque, which means I'm always trying to accelerate in absolute norm. If the velocity is negative, I want it to become more negative because the idea is to do a swing up. So if I'm swinging right, I push right. If I'm swinging left, I push left. That was the idea of the policy. Otherwise, if the velocity is 0, which is the last case, I apply Umax if Q is positive. And if Q is negative, I apply minus Umax. Okay, so this is the policy. It doesn't matter what the policy is actually. Here we want to implement an algorithm that, given a policy, computes a value function. So we are not going to use any of this information in designing the algorithm. And here we have a function for rendering the policy. So simply showing what the policy does in the viewer with the pendulum. And this is instead the main function, which doesn't do much. So it sets a few hyperparameters of the algorithm. So the maximum number of iteration, the convergence threshold for deciding when to stop, how often the algorithm should print stuff about its convergence, whether it should plot stuff, the discount factor, which is set to 0.9. That's going to affect a lot the convergence speed of the algorithm. Then we can play a bit with this. Then a few parameters for the environment. So especially how finely we discretize the state and the control. So those are the values that are, I think, the same that we have seen before for the discrete pendulum. Then I define the PD gains for my policy. I initialize my value function because if you remember, this algorithm requires an initial guess for the value function. And in this case, I'm simply giving a very trivial initial guess, which is 0 everywhere. And you can see the value function is simply an array with nx elements, where nx is the number of states. So how many states am I going to have in this environment?
One times 21.
Yeah, exactly. I have 51 joint positions, 21 joint velocities. So the total number of states is 51 times 21 because I can have any position in combination with any velocity. And you can see this is not going to scale well if I increase the degrees of freedom of my system. So let's make this an example. So now I have, let's say, about 1,000 states. If my pendulum would have like 2 degrees of freedom, how would this scale?
We keep it the same.
Yeah, with the same discretization.
51 squared times 21.
Square. But they're both squared.
Good.
So I will need to do basically 1071 to the power of 2. So that's the number of states for a 2-DOF pendulum. Which is about 1 million. And if I add another degree of freedom, I go to 1 billion. If I add another degree of freedom, I go to 1 trillion for a 4-DOF robot. You can see it doesn't scale well. So eventually we will need to discuss how we make this scale, because reinforcement learning in practice, we have seen it does scale to very high dimensional robots, but not if you do it in this way, of course. Okay, so after I created my initial guess for the value, which is just 0 everywhere, I call this function policy eval, which is defined in another file, which is where I want to implement the algorithm. So actually, if you want, before we do this, we can call this render policy to see how the policy behaves. Maybe we can do it a few times, just to show you what kind of policy we are going to evaluate. I see it doesn't perform very well because it overshoots. It wasn't able to stop, but it was going over the top position. It should stop at the top. Okay, this time it managed. So depending on where you start in the state space, sometimes it succeeds, sometimes it fails. Actually, more often than not, it fails, if I remember correctly. Okay, then we can comment this part and just focus on the policy evaluation. So the policy evaluation algorithm should be implemented in a file which is contained inside this sol folder. We are always inside the RL folder, but there is a subfolder called sol, stands for solutions. And this one contains 2 files for every exercise. There is a one finishing with _prof. That's the solution that is already implemented. So you shouldn't open that one. You should open the one that finishes with _sol. That's just an empty template, which is the starting point for your implementation of the solution. In case you get stuck, you can look at my solution inside the prof file. So we're going to start with this one, x0 policy evaluation sol. And you can see it's an empty function with just comments. So these comments are there to guide you in the implementation. So this one, actually, we're going to implement it together. And then I'm going to let you implement the next algorithm. So maybe before we start the implementation in the code, we can take a look at the slides from last time to refresh a bit our memory. Okay, so this was the slide on iterative policy evaluation, which is the algorithm we need to implement. So we want to evaluate a given policy pi, and the way we should do it is apply iteratively Bellman expectation operator. So we should iterate, and at every iteration, we update the value function at state x using the following expression. So the cost at state x applying policy pi plus discount factor times the previous guess of the value function, vk, evaluated at the next state. And we should do that for every state of the MDP. So basically, we need to implement this one-line algorithm. It's going to be a bit longer than one line when we convert it to code, but in math, it's very simple. It's just one line. Okay, let's do it. So first of all, we need to implement a for loop because we need to iterate. And we have a maximum number of iterations, which is specified here. So I say we do 4k in range max iters. And then we're gonna break out of the loop in case we reach the convergence threshold. So as the comment suggests, we start by making a copy of the value. We want to remember what the old value function was, so that at the end we can check for the convergence thresholds. You remember we define convergence by looking at how much the value function has changed in the last iteration. When this change is sufficiently small, we say we have converged. We don't want to reach really zero change. That may take too long. Okay, then it says the number of states in the environment is defined by env.nx. And we can use the method env.reset to set the state of the robot to a specific state. So it says so because we now need to loop over all the states of the environment to update the value function for every state. And this is very easy because the state is just living in a discrete space between 0 and 1070. So we just loop between 0 and 1070, and we are covering all the state space by doing that. So we can simply do for x in range m.nx. And so we loop over the state space. So for every state, we just set the environment to that state. And now we need to basically implement the equation that was written here. We need to update the value function based on this stuff. So env.step is the method that we need to use to simulate the system dynamics and compute the cost. So this is going to return x next and the cost. How do we compute the control input u? Yeah, that's given by the policy. So we can do u equal pi of x. So the policy was given as an input of this function pi, and it's a function, so we can just call it. So now we have everything we need. We have the control input u, we have the current state x, we have the cost, we have the next state. Now we can update the value function. So the value function, remember, is just a vector. So the value of a given state is simply v of x, where x is used as an index for accessing the vector. So v of x equal to the cost plus gamma, which is a discount factor, times v old of x next. So this is basically the equation that was written in the slide. And the algorithm basically is done. Now we just need to check for convergence. So checking for convergence, we can do something like that. R and P dot max P dot abs V minus V old. So we compute the difference between the value that we have now and the value we had at the beginning of this iteration. And we take the absolute value of this difference, and then we take the maximum of all the absolute values. This is actually a specific norm. Do you know which norm this is? One would be the summation of the absolute values. If you take the maximum of the absolute values, that's another norm.
I don't know, 0, it's just a guess.
Almost, like take the inverse of that. What's the inverse of 0? Infinity. Yeah, that's the infinity norm. And then we say if this error is below the threshold of convergence, break. And then we can add some prints just to monitor how the algorithm is doing. So we say if k percentage and print equal to 0, then we can print something like iteration k v minus v old equal error. And we could also plot the value function. So if plot amp dot plot v table v. maybe here we can also do iter k policy eval as converged, and we print also the error. Okay, so that's the algorithm. So it fits in one screen with all the comments and everything. It's pretty compact. Any doubts before we try to run it? Okay, let's move my face over here. And let's try to run this. Not a good sign. So let's see, there is a mistake somewhere in policy eval. Yeah, the policy says it's missing one argument because I forgot to pass, I think, the environment. The policy function, which is defined here, takes two inputs, the environment and the state. I've only passed the state, so it's complaining. So here it should be pi env.x. My mistake. I think I do that every year. Let's try to run again. Okay, now it's working. So let's see what happened. What you're seeing here is a plot of the value function. And at the very beginning, the value function is not super interesting to look at. What are we seeing? So on the x-axis, you have the joint angles, q. On the y-axis, you have the joint velocity, q dot. And they are discretized. So what you're seeing is basically like a matrix. And the value, you can look at the color map. It's dark blue when it's 0, and it's instead white when it's -1. So what we are seeing here is that the value we currently have is -1 when we are at 0, 0, which is the goal state, which corresponds to the top configuration of the pendulum with 0 velocity. That's the state we want to reach. And we know that the cost function there is -1. And everywhere else is just 0. That's what we have after one iteration. So we can now close and let the algorithm keep working. Okay, it didn't close. I don't know why, but we have the new figure. So after probably 10 iterations, this is what the value function looks like. It's much more interesting. We still have the white spot here, which, however, no longer corresponds to -1. Now the legend has changed, and so we have roughly -7 here. Why do we have -7 and not -1 if the cost is -1 when we are at this state? What is the value function? What are we estimating?
sum of the cost and the gamma, like
Yeah.
by the usual.
Yeah, it's the sum of the cost discounted with gamma. So here, I think we are at 10 iterations. Let me check. Yeah, iteration number 10. So it's as if we had been going through 10 time steps. At every time step, if we are at the goal state where the policy is sufficiently smart to remain at the goal state, if you start there, and if you stay there for 10 time steps, you collect -1 at every time step. So you should get -10 as a cost. But since you have the discount factor, which is 0.9, actually you don't get -10 because all the rewards, all the costs after the current time step are discounted. And so this discounted summation after 10 time steps gives you something like -7. And we can see that everywhere else, well, in most states, we still have 0. What are the states for which the value is 0? What can we tell if the value is 0 for a given state?
That the value of policy is not able to reach the final state.
Yeah. So if the value of a state is 0, it means that starting from that state, we don't reach the goal. Because we never collect anything else than 0 if the value is 0. Instead, the other states for which the value is not 0, but they are like light blue, these ones, it means that starting from these states, eventually we reach the goal. Because that's the only way we can have a value which is not 0, is by reaching the goal, because the goal is the only state for which we have a cost which is not 0, but it's -1. And what can we say if, like for instance, here we have a color which is lighter than here? What can we say comparing these two states? What does it mean that the color here is a bit lighter than it is here?
That the lighter one reaches the final state quicker compared to the darker one.
Yeah, exactly. Okay, this is the value after 20 iterations. After 30 iterations. And we can see also here, we are starting to see a bit of convergence. So the difference was 1 at the very beginning, then it got to 0.3, 0.1, 0.04. So you can see that it's going down. 0.01, 0.005. Okay. After 88 iterations, we have converged with a change of the value function, which was slightly below 10 to the -4. And the value function was the one we have seen just a moment before converging. And maybe we could also add this here. So we can see the final value function. Okay. This is the final value function. And looking at this, you can see clearly that the policy is not very good, because actually for most initial states, it doesn't reach the goal, because we can see that most of them are dark blue, even after convergence. But from some initial states, the ones that are not dark blue, it does reach the goal. You can try to improve it if you want, the policy, I mean. And that's it. That's our policy evaluation algorithm implemented, running, it's working. The only thing that I think makes sense to try is now to play a bit with the hyperparameters. What do you think is an interesting parameter to play with? I think there is only one. Yeah, discount factor, I agree. So what do you think is going to happen if I make this larger, like 95? Let me disable the plot and rerun the algorithm with a larger discount factor. So now it converged in 180 iterations. Before it converged in 88 iterations. It's exactly the same problem, same algorithm. I've only changed the discount factor. Why does it take longer to converge with a larger discount factor?
And a longer horizontal.
Yeah, basically when you make the discount factor larger, it's as if you're increasing the horizon you're taking into account when evaluating your policy. After a certain number of time steps into the future, the discount factor makes the future costs so small that they don't matter anymore. So basically you go below the convergence threshold, which in our case is 10 to the minus 4. So if you have a small discount factor, it's like having a short horizon, and a large discount factor is like having a large horizon. And of course, if you have a larger horizon, it takes longer to converge because you have to go through more steps of policy evaluation. And that's going to be true for all the reinforcement learning algorithms. The discount factor is something that is used by almost all reinforcement learning algorithms. So every time you tune that, that's going to affect the convergence speeds of the algorithm. It changes also the behavior of the policy if you do policy optimization, which we are not doing right now, but we're going to do in the next exercise. So typically, if you have a larger discount factor, that corresponds to a longer horizon, which corresponds to a better policy because your policy is more far-sighted. But that comes with the downside of taking more steps to converge. Okay, I think it's a good moment now to take a break. And after the break, we implement policy iteration, which is our next algorithm. So see you back here at 9:40. Okay, let's move on to the next exercise, which is X1, policy iteration. So this is the script. It's very similar to the previous one. It starts by defining a few hyperparameters. some of which we already had before. And then it calls this function called policy iteration, which is defined in another file where we should implement the algorithm. So in this case, we are not doing evaluation, but we are doing policy optimization. So we are given the same environment we were working with in the previous exercise, and we need to find the optimal policy, which you're going to see is much better than the one I had defined manually, for swinging up the robot to the goal state. Here we have a few more hyperparameters. We have the maximum number of iterations for doing policy evaluation and the maximum number of iterations for policy improvements, which is much lower, it's only 20. We have two convergence thresholds, one for policy evaluation, one for policy improvement. So checking how much the value has changed and checking how much the policy has changed from one iteration to the next. We use these two thresholds for deciding when we have converged. Discount factor, how often we print stuff, and whether we want to plot stuff, which I'm gonna set to true in the beginning. And everything else is the same, except that now we also need to provide an initial guess for the policy, not only for the value. So the initial guess for the policy is just 0 torque everywhere. And the way we do that is that I take the value 0, I convert it to discrete space, because when converting to discrete, it's not going to be 0, it's going to be actually 5, I think, because I have 11 values, so between 0 and 10, and the middle one is 5. And that's it. Then we call this function policy iteration, which is in the other folder. As before, this is an empty function, just filled in with comments. So before implementing the algorithm, again, we can take a look at the math. This is the policy iteration algorithm we have discussed last time. The objective is to find the optimal policy for a given Markov decision process. We start with an arbitrary policy pi0, which is, in our case, is a policy providing 0 torque everywhere. We loop, and at every iteration, we perform this two-step process. First step, policy evaluation. And for doing policy evaluation, we are going to use the algorithm we have just implemented. So the iterative policy evaluation algorithm, which takes as input a policy pi, and it gives as output the value function of that policy, v pi. So the first step is just calling the algorithm we have implemented a moment ago. Done. So the main effort is going to be the second step, which is the policy improvement step. So the policy improvement consists in updating the policy function. So we will need to loop over every state in the state space. And for every state, we update the policy using this minimization. Remember, this is a minimization over a discrete space. So how do you do it? You don't compute gradients and do Newton methods. You do something much more brute force. You just evaluate all values and you take the minimum one. Actually, the argmin. So there is a function, I think argmin in NumPy, which you can use. You pass a vector and it gives you the index corresponding to the minimum of that vector. So you will need to evaluate this expression here for all possible values of u, which in our case are 11. So you evaluate it 11 times, and then you look out of these 11 values, which one is the smallest. that gives you the minimum. And this expression is exactly the same expression we have used for doing policy evaluation before. So you should know how to compute this. And in the code, as before, you have a detailed list of comments that guide you step by step into the implementation. So I think that taking inspiration from what we have done before the break, you should kind of be able to implement this on your own. So I suggest you now you take half an hour to try to implement it, and then in the last 10 minutes, I show you how I implement it. Of course, I'm gonna stay here in case you have any question, any doubt to help you. How's it going? Did anybody manage to implement everything or some of it? How's it going for you?
Yes, but they have a error policy function, so at the very beginning.
Okay,
Yeah.
okay, but at least you implemented it.
Yeah.
Okay. Let's try to implement it together now so you can compare with what you've been doing so far. So I'm gonna try to follow the comments. So create an array to store the Q value of different controls. So I'm gonna simply create an empty array. Which size should it have? Yeah, emp.nu. So then I have a value of Q for every possible control input. So emp.nu. Then I need to iterate for at most max improvement iters. At every iteration, I need to start.
Is not defined by X, the state.
The Q function is a function of state and control, but inside this algorithm, we only need to compute it for every state. We're going to compute the Q function and then pick the minimum over all the values for the different values of U. Then we need to call the policy evaluation function, which takes many parameters. So I'm going to go in the previous script and copy it from here. I just need to adapt the name of the parameter. So the discount here is called gamma. The policy is called pi. The maximum number of iteration is going to be max eval iters. The convergence threshold is called value threshold. Plot, I'm going to pass the parameter plot, and endprint, I'm going to pass the parameter endprint. And so I get the new value. Now make a copy of the current policy table. That's for just checking the convergence threshold at the end. So I'm going to say pi old equal np.copy of pi. Then it reminds me that the number of states is env.nx and the number of control is env.nu. And I can set the robot state using env.resetx. And I can simulate the robot using the step function. So I need to loop over all the states in the environment and over all the control in the environment. Well, for every state, I need to reset the environment to be at that state. So this one goes here. And now basically I need to apply the control input to the environment to see what is the next state and what is the cost that I get. And then I can compute the value of Q. So the value of Q is simply cost plus the discount gamma times value of the next state. And so with this, I have computed the value of Q for all possible states and control. And now I need to choose what is the best action. And I can do that using the argmin as suggested here. So pi of x is going to be np dot argmin of q. And this is my policy improvement. There is an error though. This one needs to go inside here, because I need to reset the state every time before reapplying the control. Otherwise, the system keeps evolving from the state it had reached. And actually, the algorithm is done. Now I just need to implement the checking for the convergence thresholds. Which is pretty simple. I'm gonna do np.max, np.abs of pi minus pi old, and say, well, if r below, what's the name? It's policy threshold. Then I'm gonna print pi has converged at iter k, and then say pi minus pi old equal r. And I'm gonna plot the policy, and I'm gonna plot the value. And then every once in a while, I'm gonna also print some stuff just to update the user of how things are going. But yeah, I should break when it has converged. That's it, I think. Cannot be sure until I run it. Let's try to run it real quick. Python x1 policy iteration. Bad sign. Pi is not callable. Where am I calling it? Okay, yeah. There is a mismatch in the policy representation between these two scripts. So we actually need to go back. Well, to make it faster, you can just switch these two lines here. You can use my implementation of policy evaluation, which can work both with the policy being a function or the policy being a vector, because you can represent it in both ways. So if you switch to mine, it should work. Except it doesn't find it. Yeah, yeah, I shouldn't have solved there. Why it doesn't find it? Let's see. Sol underscore prof. Yeah, it has the wrong name. Yeah, okay, that's the correct one. Evaluation, sol, prof. It seems correct. Okay, no, it wants the complete path for some reason. Yeah, it's because I'm running it from another folder. org.rl.sol. This stuff. Now it should work. Okay, it does work. So you can see now the V table of the initial policy, which is printed way too often. So we should change that. Die, okay. Yeah, the problem is that when I'm calling policy eval here, it's printing stuff all the time, which is not good. Now it should be better. Yeah, okay, so it's just showing it at the end. And you can see now how the value is getting much, much better than before and more interesting, showing that the policy actually is able to get to the targets from every initial state. Okay, we have to stop here because there are people who want to come inside. I'll see you on Friday, and we keep going with the theory of reinforcement learning.